Okay, so what are we going to talk about today? It is Pythagorean's Theorem, which is a squared plus b squared equals c squared. And so we have kind of this triangle right here. So we want to kind of understand Pythagorean's Theorem, but then we also want to understand something called the distance formula. Now, why do we want to understand the distance formula? Because in the coordinated plane, Pythagorean's Theorem is the distance formula. So let's kind of think about how we can do that. We can look at our ordered pairs, and we can think of A, and we're going to put it down as 3, 1, and B as 6, 1, right? And we'll call this A, B, and C. I guess the order of the position of the I could go ABC that way or ABC this way. It doesn't really matter. But this is 3, 1, 2, 3, 4, 5. Okay, so if I want to find, say, any length, of course, the length of AB is pretty straightforward. It's 3, right? And the length of AC is pretty straightforward. It's 4. Well, Pythagorean's theorem says to take a look at the leg and to take the units and kind of think about this relationship to calculate this unknown distance right here. And so Pythagorean's theorem looks at this and goes like, okay, well, what do we get as we kind of build these squares? And I'm going to kind of build these squares here. And how many squares do I get if I kind of just build this square as I go through this? And you can kind of see that I'm getting 9 squares, right? So I have 9 squares off of this 3 thing, right? So if this section is 3, I have this big square, and I'll shade it in just so we see, has 9 squares, right? And then I can do the same thing off to this side. I can see that this is a unit of 4, so if I go 4 units this way, and and then put a top up here, and then create another 4 units here, I can kind of see that I have another square with 16 units. And of course, you can do this with any triangle, but sometimes they're rotated, sometimes they're angled in different ways, but this is nice vertical, so this helps us see that the area of this shape is 16, right? So we can kind of look at this formula. We can say 3 squared plus 4 squared, right? Because we're looking at the area, and the area will give us some equivalent area. So if I kind of go up some distance, right? And this is going to be a little tricky because I'm going to try and be as perfect as possible, but of course, this is just a kind of an estimation of about where I might find my area, right? And so this is pretty close. It's not perfect by any means, but if I kind of want to make equal size squares, I'm going to draw 1. And again, these are approximations, so you can kind of see that I'm trying to get these lines as perfectly straight as possible, but also a nice even distance, so that we can kind of keep them. But this isn't perfect, but let me see if I can fix this one just a little bit to make it look a little better. But see, now look, now I have almost 4 or 5 equal sections, and then we can do the same thing over here. And so you can kind of see how this is how Pythagorean's theorem was kind of used to make sense in a coordinated plane of segments, right? We can kind of start to see that I have 9 here and I have 16 here, and how many do I have here? I have 25. And so what it is saying is that the sum of these 2 squares should equal these squares, and I could place them all and they would fill in perfectly, which means that if I take this number right here and I square it, the square root of each side is equivalent, right? And that's what this is saying. That makes sense, which makes this side 5, because the square roots, if I kind of go back and instead of using 5 squared here and just leave it as c squared, I know it's the square root of 25, which is in fact this section here, which is why this distance is 5. Okay, so using this, and so we can use this for a general rule because it's not always that neat, but we see it in a nice neat way, so we can extend that rule to other situations, well, we can kind of think about how to create the distance formula from it. So if I think of A, and actually I'm going to use B instead, because we're going to go from B to C, because that's the diagonal. A is not really needed for the diagonal, but if I want to go from B to C and just prove this example, well, the distance formula is something you need. So we know that this is x1, y1 if I'm going from B to C, which makes C x2, y2. And if I'm going from C to B, this would be x1, y1, x2, y2. They are interchangeable. Really, they're just 2 points on the same line, so these two situations can change. This is just the placeholder of the ordered pair. So this is saying x ordered pair 1, y ordered pair 1. So that's group. So I want to know what is my vertical distance, right? And we've already calculated it, but I'm looking at the distance from here to here, right? And if I go to C, C is y2, right? Because this is vertical, and that's y. I'm going to be taking y2, and I'm going to subtract y1. And that would be the same thing as kind of this 5 minus 1, right? And then I'm going to leave it here. And then I'm going to do the kind of the same thing for x. And if I kind of look at the x-axis, I can see that I went from B to C, so I have to go some horizontal distance, and that distance is going from I'm going from B to C, so I'm going to travel from x, right? I'm going to say 3 minus 6, and that's what I would have here. I'm sorry, I don't want to put it underneath. I want to keep this consistent. This is my x2 minus my x1, which makes it 3 minus 6. If we kind of go here and look, we can kind of see that we have this 3 minus 6 here and this 5 minus 1, which is this vertical distance is, this vertical distance is that, here, kind of make it look a little bit better, which is the same distance here, which is that 5 minus 1, right? I take away this 1 unit from 5, and I'm left with these 4. And then over on the horizontal distance, so I'll kind of, I'll use a different color just so they see. I look at the x-axis, and I notice that I'm going from here to here. I'm just going 3 distance. I start at 6. I subtract these 3 units. I'm left with 3 units. And so we have this 3 here plus this 4 here. But we want to use this same format, so we're going to square this, right? And we're going to square this because we know it's a squared plus b squared will equal the length of c squared. So that means I should square this here. 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 And this would equal c squared, which means that if I take the square root of this side right here, I would take the square root of this side, right? And so over here I am left with 9 plus 16, and we've already done this problem. I'm not going to go through all of it, but mathematically speaking, right, 3 squared is 9, 4 squared is 16. We get this 25, which is the length of c, which is the distance. And so we can call this the distance squared is c squared, right? But since we want to find the length, not the area, if we take the square root of this side, we do not need to leave the 2 there. And so now we created the distance formula, where distance is the square root of the distance between 2 x values squared plus the distance between 2 y values squared. Okay, and so this distance formula is exactly the same thing as Pythagorean's theorem. It is used in the coordinated plane. And so if you get an example, and I'm going to pull over one right here, this looks very similar to other things that maybe you've done in the past, but here is a question where we can kind of see this distance, this x distance. Here is my original ABC triangle, and I'm building a right triangle off of it, right? So how do I know if this is a right triangle, though, to evaluate before I even begin going to determine? So assuming it's a right triangle, then I can do this. But what if I don't know if it's a right triangle? how do you determine if you have a right triangle? Well, if the legs intersect at a perpendicular angle, okay, then you have a right triangle, right? So let's just look at the slope of this. Up 1 over 1, up 1 over 1, up 1 over 1. So AB slope is 1. And if I go from B to C, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, BC slope is -1. So they meet the characteristics of what forms a right angle. Therefore, this intersection is a 90-degree angle. Therefore, this is a right triangle. And I can then use Pythagorean's theorem. Now, should I use Pythagorean's theorem to solve this? Yeah, why not, right? Because I know this is a diagonal of this big triangle, I can form a little right triangle off of it and just do 3 squared plus 3 squared, right? So I'm actually trying to find the segment of this triangle here. Okay, I'm trying to find this segment. I'm trying to find this segment. I'll use a different color. And I am trying to find this other segment here. So if I can find all those segments just by using Pythagorean's theorem. Well, we've already created this situation. So this unit is 3, right? I can form right triangles in the coordinate plane every single time. So I know that it is the relationship of this, instead of using the distance formula, which we have been taught, right? Which I'll put here just because it's not here. X2 minus x1 squared plus y2 minus y1 squared. I could use that, but I could just use Pythagorean's theorem. So a squared plus b squared equals c squared. So 3 squared plus 3 squared equals c squared, which in this situation would be ab squared. So 9 plus 9, which is 18. So the square root of 18 is the segment length of AB. We can factor it to get the square root of 9 times the square root of 2, or 3 square roots of 2 is segment length AB. So that's that length there. And then what about CB? So I can use Pythagorean's theorem, right? And I can build in the coordinate plane. I can just build right triangles off of any segment just by drawing an intersecting right angle, right? And now I've built a triangle with BC, and I could call this F, whatever. So BFC is another right triangle. So 4 squared plus 4 squared, right? That's right. This is 4. This is 4. So 4 squared plus 4 squared will equal BC squared. So the square root of that, which is just the square root of 32, which is 4 square roots of 2. Right? You could evaluate that. So this is the square root of 32, which is BC, and then I could factor it to 16 times 2. I pull out a perfect square factor if you watch one of the other videos, and you will see BC. Now I want to also find AC, right? And again, I can go over 1, right, and up some units. So 1, 2, 3, 4, 5, 6, 7. So this is 7 units. This is 1 unit. Again, Pythagorean's theorem. 1 squared plus 7 squared will equal AC squared in this situation. AC squared. So 7 squared is 49. So this is the square root of 50, which I know to be 5 square roots of 2. And in fact, this is actually a proportional relationship of the 3, 4, 5 triangle, all times the square root of 2. So this is just the beginning introduction of how the Pythagorean theorem and the distance formula really interact. And this is a nice quote by Albert Einstein.